Okay, in college algebra, these are the functions we want to know. Your basic functions, or we'll call them parent functions. Then we're going to work with these. We're going to do what's called transformations with these. Okay, so your basic function y equals x, slope 1, intercept 0. Your basic quadratic function y equals x squared, parabola. Square root function, domain and range are noted here. Everything's positive. Positive values for x, positive values for y, 0 included. Here's your basic rational function. Division by 0, not going to happen. We're not going to have an output when x is 0, but we have an output for all other values. And you can see what happens as x gets big, y gets small, right? 1/2, 1/3, 1/4. The larger x gets, the smaller y gets by taking its reciprocal. And then these we're not going to worry about yet. We'll get to these later, the exponential functions and the logarithmic function. We'll worry about those later, but we will look at the absolute value function. We have a line, slope 1 for x greater than 0, slope -1 for x less than 0. We have a nice V shape right at the origin there. Okay, so study those. What are we going to do with those? Well, let's take a look. Basically, we're going to apply different transformations. Okay, so our first translation is a vertical shift. That is, if I just, what does this mean? F of x plus c. It just moves the whole graph up c units. F of x minus c, the whole graph of f of x down c units. Okay, and then we have our second translation, which is left and right. This one's a little backwards. I'll explain why. If I replace x with x plus c is going to move it to the left. If I replace x with x minus c, it's going to move it to the right. Okay, so you can see my first, so let's focus on this one right now. My first translation, how does that work? Well, you can see it by its graph. That is, here's your, if your original function, f of x or g of x or whatever you want to call it, which is x squared, right? So if I had another one here, -2, -1, 0, 1, 2, just square all these numbers. 4, 1, 0, 1, 4. What happens when I subtract 3? It's literally just going to subtract 3 from all of these, right? So 4 minus 3, 1 minus 3, and so on. Same thing here, x squared plus 3. You still do the squaring first, and then you just add 3 to all those. Pretty straightforward. What's that look like on a graph? Well, it just moves it up and down, right? Your dotted line is your original graph x squared. That's why we need to know those parent functions. That's my parent function. And just move it down 3. All the points. X squared plus 3, just move it up 3. All the points. Easy. Okay, here's a different one. This one's a little trickier. So I want to focus on this. That is x minus 3 squared. Why is that 3 units to the right? What happens there? Well, I like to just focus on this point right here. So my function f of x equals x squared, right? That hits the origin. That is input 0, output 0. So I know that's going to be right here, and then it does the parabola thing. So the question is, what happens when I take out the x and I replace it with x minus 3? So now I'm looking at x minus 3 squared. What does the graph of this look like? Why am I saying it's 3 units to the right? Well, one way to think about that is where's the intercept on that guy? So if I wanted to find the intercept, I would take my function and set it to 0, right? So you can square root both sides if you want to do the algebra. And then I add 3. Here's the key step, add 3. I've now found the intercept. It's when x equals 3. So on my graph, that's right here. So I know that only shows you for one point, but I know that's the intercept. I know this graph is just hitting the y-axis at one point, so the rest of the points should follow. So it's a 3 unit shift to the right, not just for the what we call the vertex, but for all the points on here. And I can show you this for all of them. So I was just talking about this function, but it's all the other ones too if we did it. We get all those other points, and the whole graph would be shifted to the right. And then we could do the same thing for replacing x with x plus some number. It'd be a shift to the left. Okay? Moving along, we got their next transformation of reflection. If I just have my graph, like f of x equals x cubed, that's my dotted line. Oh, we got to add that too. I just realized I don't think that was on. That should be on here. I'm going to add that to this graph. We need one more cube function. And the cube function is y equals x cubed. And what happens when I cube numbers? 1 cubed is 1. 2 cubed is 8. Negative 1 cubed is negative 1. Negative 2 cubed is negative 8. So you've probably seen this one before. This isn't the best graph. I just want to give you an idea. Try that again. It should go, something like that. Okay, so let's add that to our list of parent functions that we should know. And if I go back to my lesson, here's a little bit better graph. The dotted line is the cube function. And then what happens when you just put a negative in front of it like this? Well, it takes all these positive values and makes them negative, sends them down here. And vice versa, if there is a bunch of negative values on the graph, the y values, and you just multiply them all by a negative, it sends them all up here. They become positive. So it's a reflection around the x-axis. That is, if I put a negative in front of my function. All right? So how would you graph this one? Our first example, graph y equals negative root x. So you know your parent function. Input 1, output 1, input 4, output 2, square. We could do a dotted line if we want. I like to graph the parent function and then do the transformation. I'll use a different color. Let's go with red. So here's my answer. It puts this point down here, reflects it around the x-axis, right? It points to this point here. Whoops, too far. And the red graph is my answer. That's it. It's a reflection around the x-axis. Okay. We also have this guy, a reflection around the y-axis. So that is, let me give you an example of that. If I had, let's say we had the function. Well, let's look at my parent functions. And let's see what would happen with one of these guys. Oh, how about 1 over x. Let's reflect that. Let's do that one. Okay, so your goal is to graph. If I give you f of x is 1 over x, and then the question would be graph this function. Let's call it g, and it's 1 over negative x. All right, that's what this means. That means I plug in a negative x. So according to this, it reflects over the y-axis. So if my original graph is my parent function. I was using a dotted line before, but let's just say this is my original graph, 1 over x. And when you replace x with negative x, it reflects around the y-axis. Okay, so my new graph, let's use red. Here's the answer. It's that simple. I don't have to find points. I don't have to do anything but just do the reflection. This comes over here, and this point would be over here, and all the points that follow. So that is my function g of x, which is 1 over negative x. Okay? What else we got? Horizontal and vertical scaling. So if you multiply a function by a number, it stretches it out as long as that number is greater than 1. If it's a smaller number, it's going to make it smaller, right? So c times the function. If it's 1/2 of x, it'll cut it in half. All right, so here's a couple, this would be examples of that. And then my final ones, hang in there with me, I got one more. If I plug in, and then we'll do some examples and it'll clear all this up. If I plug in, if I replace x with c times x, then we have a horizontal compression or stretch. All right, so again, best understood by example, the blue guy is x squared. If I plug in a 2x, and then my function is now 2x squared, which would be equal to 4x squared if you multiply it out, you get this horizontal compression because c is greater than 1. Likewise, if you plug in a number less than 1, and you plug it in for x before you do the operation, 0.5x squared, which would be, that's 1/2 x squared, so you would get 1/4 x squared, or in decimals 0.25 x squared. That's going to be a horizontal stretch. All right, in my next video, we'll do a bunch of examples.